In this video, we are going to talk about molecular polarity. Electronegativity is the ability for an atom to attract the electrons to it within a bond. So remember, in a covalent bond, electrons are shared, and sometimes they're shared equally, sometimes they're not shared equally. Electronegativity allows us to look at how those electrons are shared. Now, when we don't have equal sharing of electrons, we can talk about it in terms of polarity. So, polarity is determined by the difference in electronegativity between two atoms. And here is a table of electronegativities. Fluorine is the most electronegative atom, and it decreases as you go down and across the periodic table. So, francium is the least electronegative atom. We have two types of covalent bonds. A nonpolar covalent bond is going to happen when the difference in electronegativity is less than zero point 0.4. So for a nonpolar covalent bond, we say that electrons are shared equally. If you get a difference more than zero point 0.4, then we are going to have a polar covalent bond. And this happens when electrons are not shared equally. If the difference, so delta is change, the change in the electronegativities, the difference in electronegativities is greater than 2, then you have an ionic bond. If you're trying, so I want to be very clear, this is only for bonds. In a molecule, we have a lot of different bonds, but you can determine the bond polarity using this method here. For a molecule, you have to look at the entire molecule. So first you can look at the bonds, and then you can look at all of the bonds within the molecule. And you can't do that without looking at the geometry. So the geometry of the molecule has to be considered. So when the electron density is pulled equally in all directions, another way of saying that is electrons are shared equally. The result is a nonpolar molecule. When electron density is unequal or it's pulled unequally in all directions, another way of saying that, electrons are not shared equally, then the result is a polar molecule. For this class, a way you can really determine this is just look what that central atom is bonded to. So look at the central atom. If the central atom is bonded to all of the same outer atoms, well, actually, let's say to outer atoms that are all the same, and there are no lone pairs, this is important, on the central atom. Then the molecule will always be nonpolar. So I look at my central atom. Here, I look at my central atom. Is there a difference in electronegativity more than zero point 0.4? Absolutely. Between carbon and oxygen, there definitely is. So the electrons are always going to move towards the more electronegative atom. So that means they're going to shift from the carbon to the oxygen. However, those shifts are happening in equal and opposite directions, so they kind of cancel each other out. So our molecule is going to be nonpolar. And if we check this rule right here, I have my carbon. There are no lone pairs on my carbon at all, and it's bonded to the same outer atoms. It's going to be nonpolar. If you're looking at a polar molecule, you're going to look at the central atom again. If it is not bonded to outer atoms that are the same, so there are different atoms that it's bonded to, or if there is a lone pair on the central atom, then the molecule is polar. We can look at an example of this, SO2. Here, my sulfur is bonded to the same atom. It's only bonded to oxygen. However, I have a lone pair on my central atom. So this molecule is going to be polar. Let's take our practice problems from before and determine if the molecule is polar or nonpolar. The first thing I'm going to check is my delta En. You can use the table of electronegativities to calculate your delta En. When you're calculating the difference in the electronegativity, you're really just looking at the number and not the magnitude. So if you get a negative number, that's okay. You can just take the absolute value. So I'm looking at carbon and hydrogen. So I have 2.5 minus 2.1, which is 0.4. There's not a big enough difference in electronegativity. So there's no movement of electrons, which means electrons are all shared equally. This is going to be a nonpolar molecule. We can also know it's a nonpolar molecule because my central atom is bonded to 4 atoms that are all the same. And I do not have a lone pair on my central atom. It is a nonpolar molecule. With water, the electronegativity of oxygen is 3.5, and then hydrogen is still 2.1. So my delta En is going to be quite high. So I will get a delta En of 1.4. So this is definitely a polar bond. So I can show that by saying that the electron density is going to go from the hydrogen to the oxygen. When people draw these out, they think, oh, they're going in equal and opposite directions. They're going to cancel themselves out. However, this does not show the geometry. This only shows the 2D representation. We have to remember that this is a tetrahedral molecule, which means I have my oxygen here. One of my hydrogen is going to be going down here. One of them is going to be going up. And then I will have my lone pairs, one of which will be coming out at me and one which will be going back into the page. So now we can see that we don't have the electrons moving in equal and opposite directions. So this is going to be a polar molecule. Another way of looking at this is my central atom has lone pair electrons on it, so it is going to be polar. Let's look at these two examples. We do have a polar bond here. In this case, my molecule is linear because I only have the two things around it. So they will be in equal and opposite directions. This is going to be a nonpolar molecule. Additionally, the carbon is only bonded to oxygen. There's no lone pair, so it's going to be nonpolar. With ammonia, we know that it is also tetrahedral, and there is this lone pair. Yes, this is going to result in a dipole bond, or this is going to result in a polar bond. However, all you really need to look for is that lone pair of electrons on that central atom. So ammonia is going to be a polar molecule. For carbonate, I have my central atom, and I have the same atom bonded to my central atom. So this is going to be nonpolar. In my next example, formaldehyde, I can see that I don't have any lone pairs on my central atom. However, I don't have the same atom bonded around my central atom. So that means this is going to be a polar molecule.